This is Module 9's lecture on Introduction to Coordinate Geometry and Area Calculations. I say introduction because we're not going to the full depth of what that involves in this class, or even in Surveying 2, because it can be a very in-depth process. If you are planning to sit for the FS exam, you will need to obviously take Surveying 2 and become very familiar with advanced coordinate geometry operations and the formulas and how to apply them and such. In Survey 1, we're not going that far. This is more of an introduction to both introduce engineering students to the concepts of area calculations and coordinate geometry, and also to lay somewhat of a foundation for the S2 course. So in the book, section 11.1 speaks pretty well about what surveying calculations do. We use coordinates. I will point out again, and we'll repeat it a few times, that the book uses the traditional mathematical formula of X and Y. Surveyors reverse that and go north and east, which is basically YX. So we'll have to address that in some other lectures or videos. We will just touch basically and briefly on the topics here, and I'll probably provide some additional videos to illustrate some of the more simple and common survey calculations, such as bearing intersects, maybe a distance intersect, and some area computations, the various methods there, and a double meridian distance. The more advanced aspects of resection and some of the other topics that are covered deeper into both chapters 11 and 12 will be omitted from this module. Most everything is going to come back to something like this. This is illustrative. It's figure 11.1. It's an oblique triangle. This is basically what we do every day as land surveyors. And we refer back to, this is why it's required to have a math prerequisite for this class that covers trigonometry and some college level algebra, because as you can see, formula 11.1 is the law of sines, 11.2 is the law of cosines, and 11.3 is the quadratic equation, which is our quadratic formula derivation that is used in this. In section 11.2 and figure 11.2, we're basically looking at the geometry and the coordinate forms of equations for lines and circles. 11.4 is how to compute the length of a point using the latitude and departure, or the difference y and the difference x. And this illustrates it here. This is all coming back to college algebra and trigonometry. M here being the slope of the line through points A and B. And they've added in an additional point P. But basically what we're trying to do is define this line. And so we've got A and B and P. And the slope of that line is basically also equated to the azimuth. So there we are. I don't really understand what B means, but I guess that's the height above the x-axis of where this intersects the y-axis, which does tie back into some of the quadratic equations from college algebra and trigonometry. Because so many surveying projects include aspects that have circular curves, coordinate geometry is pretty heavy into circles, because an arc of a curve like you use in a highway project, even a taxiway or a runway project, all all the time in subdivision designs, street alignment for new subdivisions and new road projects. We're using arcs and circular curves, and arcs are just a portion of a circle. So all of our arc formulas and everything that we'll go into later, we'll touch on in this class. They'll be expounded on much more deeply in Survey 2. Is each of those arcs is a portion of a circle, so circle formulas apply. Now, one of the more common problems or exercises that we might do as land surveyors is that people want to know how far from a certain line is a certain object. And that's always going to be a perpendicular distance because that is the closest distance. And this may be how far is an iron pin or a house or a certain encroachment or feature or utility aspect from a property line to where the line is defined by 2 points in the boundary survey. It may very well have nothing to do with a boundary survey and be a pipe alignment project, and needing to know if that same object is within the construction easement or how far away it is, so that there may be evaluations by the engineers as to soil stability or back slopes during excavation, how far they will go back and what they will impact, as well as along a road project, right-of-ways often offset certain distances from a center line. There are also cuts, fills, drainage features. So it takes us to figure 11.4 in section 11.3, where this is actually pretty simple. So we have the point A and B. He's saying that there's some block corners out here that may have created A and B. That's fine. And then point A is not necessarily at the 0 value of the x-axis along the y-axis. It's just a point that's out there. And so, if you've got these 2 block corners which define the line, and you're on that line at a point A, you can determine the interior angle, little a, to point P, which has coordinates x sub P, y sub P, and then basically it's not horizontal, but it's similar to total station elevation or trigonometric leveling function. You've got you don't have the zenith angle, but you have this interior angle. Multiply that times, or you got the angle A, and you'll have the distance A to P. The math can help you solve to what is B using these formulas here in section 11.3. And again, these are some things that we'll give more examples to, and I would also encourage you to look at some of the problems at the end of the chapter and work those. 11.4 is the intersection of 2 lines, both having known directions. Now, you'll remember from coordinate geometry or from geometry class that two lines that do not intersect are parallel. If they do intersect, then they're not parallel. So this section 11.4, figure 11.5 is a good example of a survey problem that you might run into. He's shown a prism pole at P, which sort of detracts from the example here. Usually point P would be an inaccessible point. Perhaps it's on the other side of a fence, it's on someone else's property that you cannot trespass on, but you need to know where this point is. The point down here where the rod is sitting, let's say that's a corner of a concrete wall or a building corner or something. Well, you can come back over on your side of the property line, set up a baseline basically on A, here underneath the instrument, and B, and turn angles from A and B. In this case, they're really just pointing out the azimuths, but regardless of how you do it, once you've set up and you've turned an angle between A and B, like A backsiding B, turning to P, you've got that angle. You can measure the distance between A and B, You can measure the angle between, at B backsiding A to P or vice versa so that you get this interior angle, and then there you've got it. You've got two interior angles and the distance of one leg. So at that point we're back to the section 11.1 where we've got the length of one leg. We apply the law of sines. You have the length of one leg and an angle that is opposite. And this is similar triangles throughout, so the law of sines is the same mathematical relationship at each angle point. So you can compute, knowing that we have the number of sides of this triangle is 3 minus 2 equals 1 times 180. Once we've got the angle at A and the angle at B, we can compute the angle at P. And we've got the leg distance opposite of P, so now we've got the law of sines set up. We can turn right around and compute the distance from A to P and from B to P using the law of sines, and then we can create a coordinate and check our math. This is also more commonly known as a bearing-bearing intersect. And there's another slide we'll get to in this chapter momentarily, but this is very common. If you've got two lines set up and you need to know where they intersect, whether that's where a road, a storm line, a sewer trunk line, and an interceptor intersect, once you've got two lines defined, this is how you determine the coordinates of where they intersect. And like everything else, software does this. We're teaching the theory of the math of how it works. This is also how you will find it on your FS exam, is no software, just angles and trigonometry for your NCSS approved calculator. Now we'll move on to section 11.5, figure 11.6. Because we deal with curves so much, like I was just saying, in any kind of road, and railroad is a different topic, but they have circular curves. Anytime we're dealing with a circular curve and a line, we may very well be trying to figure out a lot about how they intersect. And so 11.6, a line intersects a circle like this in two places, unless it's perfectly tangential, which means it just touches at one point where it glances off, where the line becomes the perfect distance from the radius point, which is something that we have in a curvilinear horizontal alignment of a road. But here, this is just a simple example of a line intersecting a circle, which it'll intersect at 2 points. The reason I point out, and the book points out, that this is at 2 points is more than likely, if you're trying to solve for this, if you have line AC defined, and in practical application with software that's going to be having coordinates on 2 points, you can back that into the formulas in the book to determine how that line is defined. And then you've got circular equations with point B right here of a known radius R. You may know full well that you're right here, but you'll get two solutions, P1 and P2, or point 1 and point 2. So this is important to understand that when a line intersects a curve at 2 points, you've got to use some common sense and understand, is it 300 feet away from A or is it 600 feet away from A? Well, if you were guessing 250, it's definitely not P2. And somewhat conversely or related is section 11.6, figure 11.7, the intersection of two circles. Circle A and circle B will intersect at 2 points. This is called a distance-distance intersect. P1 and P2 are both RA from A and RB from B. You'll see that the two circles coincide at 2 different points mathematically, and the formulas will give you both options, and you'll just have to decide which one is applicable. If you know that it's closer to due east from point A and closer to due south from point B, it's pretty easy to figure out. And most software will plot each option and let you choose which one is it, and it's very obvious to you which one it is in a real life scenario. We're skipping section 11.7 and 11.8. That's more advanced and not quite as applicable. And before moving out of chapter 11, we're going to look at section 11.9, which is the inaccessible point problem. And that is figure 11.12. So we talked about the bearing intersect, but what about when you need not just the location, but the z-value or the elevation of a point? So it just gets three-dimensional, but it's like anything in surveying. If you just stop and think about it and apply trigonometry where it needs to be applied, the solution will become fairly evident. Here we go right back to point P, which is our unknown point that can't be occupied, and we're turning angles and locating it from point A and B. So we've already covered how to horizontally determine the elevations of the base of P. Now, then, that also gives us the length of B to P and the length of A to P. We basically just do the same thing, knowing that, assuming the height is perpendicular, we turn a zenith angle or a vertical angle, as in the illustration, from A to point P being the top of this smokestack. And we do the same thing from B. That's this line, and then the line from A is here. But they intersect in space at only one point, the top of P. Now, the most common way and easiest to explain and easiest to understand way to determine this, in my experience, is not to necessarily use the formulas in the book per se, but again, just apply common sense and trig. And once you've got that, once you've got the length of A to B, and you've got this zenith angle, you can solve for the triangle, three-dimensional triangle, just like trig leveling, from where point B is level with the smokestack, and you don't measure this slope distance, but you can compute it using the law of sines, and then you can get this height that P is above B, and B is a known elevation with an HI. So you take the known elevation, add the HI, add the computed C value, and you have an elevation for the point P. Now, the reason you do this twice is always to have a check. You would replace this, or repeat the same procedure at A, and you would compute, the distance that P is above the horizontal plane through A. Take the elevation of A, add the HI of A, add this computed Z value, or difference in elevation, and that will also give you a value for P. And it's not going to be exactly the same, just due to the error that we encounter in surveying equipment and our eyes, and perhaps even the smokestacks moving some. If it's a very windy day or something, not very likely, but you'd be surprised how much large structural objects actually do move and flex. So let's say that this computation comes up with 87.12 from A and 87.16 from B. If 0.04 of a foot of deviation is within your acceptable tolerances, which it likely would be in a smokestack, just take the average and say it's 87.14, and then you're within 0.02 of both observations. The next slide in this presentation is an illustration that applies to problems 11.12 through 11.16. Not assigning those problems. If you are planning to pursue license as a surveyor, I would encourage you to take these problems and work through them. And if you have problems with those, please email me, but you should be able to work through them. I do have some material that and some solutions that I can share, and we could work through them. But that would be a good foundation for Survey 2 if you're planning to take that class. Closely related is Chapter 12, which is area. Remember, from geometry we have lengths of area, lengths of distance, units of volume. So all of these are just different units, and then they're different types of measurements. And let's put that into perspective. Square feet, a 1 foot by 1 foot square, like a floor tile, that's 1 square foot. 2 of them is 2 square feet. 3 of them in a row is 3 square feet. 2 of them is 2 square feet. And you can also prove that by saying that that rectangle that's formed by 3 of those tiles together is 1 times 3 equals 3 square feet. That's about the only simple example you're going to run into in surveying. Now, this is equating feet to meters squared, which is fine. If you need to know meters squared, then this is the reverse. Yards to meters squared, we're not really dealing with the metric system in this class or in the United States, but this just shows that there are ways to convert. And we have more applicable area units and conversions in the United States, basically being acres. And 1 acre is 43,560 square feet. Hectares are not used very much. I think some parts of the country may have some hectares, and also I believe Farah is a Spanish unit that you might find in Florida or Texas. But basically, you know, a yard squared is 3 feet by 3 feet, so it's a very simple conversion. 1 yard squared equals 9 square feet. You know, so you may run into that. And this is just important to keep in mind as you get into volumes later. Figure 12.1. And oh yeah, in dealing with U.S. public land surveys and even old surveys in Georgia, 10 square, you'll run into 10 square chains or 10 gunners chains or the unit square chains. And for example, "40 chains by 40 chains is 160 acres. And that's a 160 acre land lot in some parts of the state. And it's part of Sir Edmund Gunner's mathematical system that he came up with in Old England. It's basically the number length times the width, and then you drop the last number. So 40 times 40 is 1600, but you drop the 0 and it's 160 acres. 20 times 20 is 400, drop the last 0 and you've got 40 acres. So 20 chains by 20 chains is a quarter mile by a quarter mile. It's that's 20 acres, or excuse me, 20 chains by 20 chains will give you 40 acres. And you know, a full section is 80 chains by 80 chains. That's 640 acres. 6,400 drop the 0. But here, this would be something that you might just encounter. This form here of A, B, C, D, E, F, G, and then a water boundary would be a very common boundary survey issue that you run into. And the easiest way, in some ways, or at least the easiest way to visualize area of a complex shape like this is to break it into triangles. And not just triangles, but also easily definable points, like a rectangle or a parallelogram or trapezoid or something that you might see. But typically triangles is going to be the easiest way. They'll talk more about area of irregular boundaries over here. So you would solve for G to A, and you could come up with a pretty precise area for the A, B, C, D, E, F, G, A form, and then we would estimate or independently come over here to J, K, L, M, and H, I and compute these other shapes over here up to the water. Some of that's basically area by offsets. So like from station 0 to 50, that's 50 feet. It's 5.2 feet high. The area of a triangle is 1/2 the length times the height. So that's 50 feet times 5.2 divided by 2 will give you the area there, which would be 50 times 2.6, which is 130 square feet in this form between station 00 and station 50. B is 50 feet in all of these, and you would basically just take the average, 8.7 plus 5.2 divided by 2, (6.95) times 50. the area between 050 and 0100 is 347.50 square feet. So you can go along and figure the area within this choppy line by station. And what you're really doing there is probably not a choppy station that has a sharp bend every 50 horizontal feet along alignment center line. It's probably a curved or irregular shape, just like a stream or an old roadbed or a yard or a cultivation line, some kind of historical boundary or buffer. And it's the same thing. So you're not going to be uniform 50. This is a little bit more advanced, and more common example, where you've got this point and this point, H1, 2, H3, 4, 5, 6, and you will approximate just say here from H4 to H5, I'm trying to draw that a little bit better illustration. I might exaggerate it a little bit, but you're going to draw a line from H4 to H5, and basically you're approximating the area. It's not going to be precise, but in theory, whatever you gain up here above the line, you lose it back over here. And it doesn't even have to be in one line. That's kind of a handy example. But between H3 and H4, you're actually overestimating, as you can see. And here you're kind of cutting it short because the area outside of H2 to H3 is not being accounted for in the curved boundary. And curved boundary is not a real good way to describe that, in my opinion, because if it's a curve, then there's circles and there are circular formulas that we could apply. I say this applies to an irregular boundary. Now, just like with our traverse lab, where we're computing coordinates on points from our measurements, we will have coordinates on points, just like this. And what you can do here is break this shape, this A, B, C, D, E, F form into various geometric shapes that you can solve. The coordinates become, this is just assuming that you've got some, it's really not assuming so much as it computes in a vertical line and a horizontal line, or a due east, due north line. And then the figure that's being computed here is actually A to B to C to D to E and back. And let's draw that again, like say in green. A to B to C to D, D to E, and then back down to A. So this is the start of trying to determine the area. You can determine the area between D primed over here on the y-axis and C prime down here where they intersect at the same. In other words, C prime will have the x or east value of A and the north value or y of C. So this becomes the due north and due east line that forms it over here. You can also use that to very easily compute the area between D prime, D, C, C prime back to D prime. And then you would compute this brown area here between A and D prime over to the AD line, subtract that off. You can compute the area, because then you've got B prime pretty easily defined by just taking the y or north value for B and carrying it over here to the same x or east value of C prime, which is A, and you've got a triangle. And you've got the length and the height just by subtracting the coordinate values. So this is breaking, this method is pretty easy to do by hand when you have coordinates on all these points, because you can solve for a greater, larger value and then start subtracting off of it or adding back to it as you need to. And so we have a similar problem or situation here where you might be trying to incorporate a whole lot of things into one function. You've got coordinates on A, B, C, D, and E, and here A and E are parallel with G and F, so we're trying to do an area computation, maybe a 2-acre cutout or some odd area to where we're trying to solve for this line right here. That's something that would be a little bit more advanced than what we're going to cover in this. But then we're going to move to section 12.6, which is area by double meridian distance method. And this will be expounded upon more in a different lecture and video that I'll provide. But basically, going back to that same form, the double meridian distance method, or DMD, by multiplying your latitudes and departures, because your coordinates don't really matter, because your coordinate value can be based on state plane or assumed 0, 0 or assumed 5,000, 5,000, and the volume or the area of your shape is not going to change. What we are looking at is the latitude and the departure, just the local difference, the relationship from one point on the form shape to another. And so the latitude and departure, you cross multiply, again this will be brought up more, where you cross multiply and then take the sum, divide it by 2, and in this figure you get, basically the way the math works, you get double the area. That's why they call it double the meridian distance. And so you got to divide it by 2, but it will give you the acreage, or the area of a form. And so the double meridian distance method is something that we'll cover a little bit more after this lecture concludes. And this is covered pretty well in the book. Section 12.7, you have to consider the area of parcels with circular boundaries. And so this is again going back to the same form, the way double meridian distances work. Now this is the area with a circular curve as part of a boundary, and we see this a lot anytime we're along a road or a subdivision where there's a circular boundary. So basically what we do is use the geometric formulas for circles and areas of circles and areas of the part outside the circle. Here we would go A, B, C, D, E. Instead of going straight to F, we would probably wind up going to G and then F, so that we're going to be adding part of this circle. So once you find the area of the straight lines, you lay that aside. This angle theta here, you would divide that by 360, and that is the portion of a circle that you've got. Pi r squared is the area of the circle, so you can use you can determine the area of the whole circle, and then take the portion of that circle that we want to know what it is up in here, which is this, and there you'll have it. So there's also formulas for the sextant, or the exterior part of the curve right here that's outside of that. So you could go from A to F and have that area, and then figure the sextant area and add it in instead of the whole arc. But just like everything that I've hopefully tried to tell you, almost anything in surveying, you have various and sundry ways of computing things that, as long as you do it right, will come up with the same answer as if you solved it another way. This is a very typical problem that you would see on the FS exam. They would probably give you coordinates on some of these points, A, F, E, and D, tell you the radius, and have you compute the area of this form. It'd probably give you the rest of B, C, and D, and you'd have to compute the area of the remainder. Table 12.4 is another example that I thought we'd covered on area of double meridian distance, DMD. And this also seems a little redundant. It goes back to the other form that we were looking at, to where this is just an illustration of the depth of this line H to do a area cutoff, to where you can determine Once you determine the length of H, you can do some intersects and compute the positions of F and G so that you can do the partitioning of lands. Now, that was covered in section 12.8. We're going to skip 12.9 because nobody does that anymore. Or if you do, you're digitizing it and it's a CAD function, not really a surveying function. Nobody digitizes or uses planimeters anymore. We're not going into specific software. Section 12.12 is worth mentioning. Mistakes that are made in determining area calculations. The most common one, number one, is to forgetting to divide the double meridian distance sum by 2. Confusing the sines and cosines of coordinates. Reversing latitudes and departures. Number 3, forgetting to repeat the coordinate of the first point in the area by coordinate method. You have to start somewhere, kind of like a traverse, and come back to that same point. Some people will make the mistake of going from 1 to 2 to 3 to 4 and saying, now I'm done. No, you have to take that back to 1. Number 4, failing to check an area computation by a different method, just like in the circular curve portion there. You can compute the angle of the curved portion of that boundary 2 or 3 different ways, and it's a really good idea to get a couple of different ways to check it, just like the elevation of the smokestack. Number 5, not drawing a sketch to scale or general proportion, which we're going to do general proportion if we're doing it like in this class and with a calculator. You would be to scale if you did it with CAD, so that you have a visual check. You know, sometimes it just makes sense. Oh, this is 200, this is 200. Well, roughly speaking, my area should be around 40,000 square feet. If I came up with 137,000, I probably did something wrong. And a good sketch to visualize comes in handy, whether if it's on a screen or on a piece of paper. Number 6 does not apply because we're not dealing with planimeters. Again, this is an overview of coordinate geometry and area calculations, chapters 11 and 12. We will expound more with some other information, but that covers the gist of what we're doing in this module. Thank you.